So at the moment we are in the middle of discussing Compton scattering in quantum electrodynamics as one of the typical QED processes, one of the most important ones. And here I wrote down the end of the last lecture, where we first discussed the matrix element TFI for the scattering amplitude of Compton scattering. And then we discussed the square of this matrix element to provide us with the probability for scattering. And we wanted to analyze the unpolarized situation where we do not care about the spin of the incoming and outgoing electron and photon. And first we analyzed only what happens if we sum over the possible spins of the photon in the initial and final state of Compton scattering. And in order to do that, we needed to go.
طبعا أنا يعني أريد أن أقول شيئا هنا أن المعادلة الأخيرة ظهرت فيها جي ميو وجي ميو، وكما رأينا في الفيديو السابق للفات أن جي ميو في معادلتي أو في نظريتي تلعب دورا محوريا، ليس هي عبارة عن واحد أو سالب واحد، لا، هي تلعب دورا محوريا جدا جدا، فهي تعبر مباشرة عن التايم دايليشن والتايم كونتراكشن. وبالتالي أينما وجدت جي ميو في أي معادلة تخص الكيو اف تي، هذا يعني أنها لها تأثير قوي جدا في المجال الجاذبي، لأن نظرية تتحدث عن كوانتم جرافيتي. إذن جي ميو تلعب دورا محوريا جدا في المجال الجاذبي، ويجب أن ننظر إليها بهذا الأمر. ويجب أن نعرف أن الجي ميو تنقسم، هو ليست تنقسم، هي تبدأ من الأعلى وأكثر إيجابيا أكثر موجبا وتذهب إلى السالب إذا كانت الجاذبية عالية، أو تذهب من السالب إلى الموجب إذا كانت الجاذبية قليلة. ولكن قبل أن تصل هذه الجي ميو إلى ما لا نهاية من الموجب إلى السالب، يتدخل الفضاء ثنائي الأبعاد غير متناظر ويحارب هذه الزيادة الكبيرة أو هذه التغير الكبير في جي ميو. بالتالي يعني نستطيع أن ننظر إلى التفاعلات المادية بهذه الآلية.
Back to these the physics of polarization vectors, and we touched the analysis of physical and unphysical degrees of freedom. So in the center of our analysis there was the so-called Ward identity, which tells us that if we replace an epsilon polarization vector by the corresponding photon momentum and multiply with the rest of the Feynman diagram, we get zero. We proved that explicitly. And because of this, when we look at the polarization sum over two physical polarization vectors, epsilon, epsilon star for one photon, and we sum over the physical polarizations, that is the same as if we sum over all polarizations, including the unphysical ones, because the unphysical ones just cancel among themselves. And therefore, there is a correct replacement rule where we replace the sum by just minus the metric tensor, which is Lorentz invariant. This is not an equality, but it becomes an equality once we multiply it with this matrix element because of the Ward identity. And because of this, the polarization sum of the squared matrix element over the photon polarizations just gives this Lorentz covariant part of the Feynman diagram, contracted not with epsilons anymore, but just with metric tensors. So that is the result of the last lecture, and so this is now the squared matrix element with unpolarized photons, and today we will do the rest, namely we compute Compton scattering also for unpolarized fermions, electrons, in the initial and final state, and we will completely evaluate this spin-summed squared matrix element and then interpret it. All right, so let us do that. In order to continue with the explicit calculation of this squared matrix element, I will give you some hints and then present highlights of the calculations but we will not go step by step through all the absolute details of the calculation, which is actually quite involved. So in order to simplify, let us write down once more this mu nu for Compton scattering, which is minus I times EQ squared times u prime bar times the following, gamma nu QA slash plus m, that will be a little short, gamma mu divided by QA square minus m square plus gamma mu QB slash plus m, gamma nu divided by QB square minus m square times u, where u is the spin order for the incoming electron, u prime is the spin order for the outgoing electron, and this square bracket in the middle corresponds to the Feynman rules for the internal vertices and the internal electron line. And there are two Feynman diagrams, and in one diagram the electron carries the momentum QA, in the other diagram the internal electron carries the momentum QB. And the two Feynman diagrams differ by the order of the photon interactions, and therefore we have here once gamma mu, and in the other diagram we have gamma nu with the opposite order. So that is our mu nu, and that is what we need to calculate. And so let me just write down a few things. So first of all, the denominators. The denominators have the following values. For example, QA square minus m square is the sum of the two incoming momenta p plus k square minus m square. And if we evaluate that, we get a binomial formula p square plus k square plus 2 times pk. Okay, but p square is actually equal to m square, so p square minus m square cancels, and k square is actually 0 because the photon is massless. And so therefore the only thing that remains is 2 times p dot k. And that is the same as the outgoing momenta p prime plus k prime, and therefore this is also the same as 2p prime times k prime. Then the other denominator, qb square minus m square, similar discussion, p minus k prime square minus m square. So again, we get p square minus m square, which cancels, k prime square is 0, and so we get minus 2p times k prime. And again, this is the same as p prime minus k, so it's also the same as minus 2p prime times k. And so we have first of all these relationships between scalar products, and we can simplify the denominators. So, and then we already see this equality, p dot k is the same as p prime dot k prime, p dot k prime is the same as p prime dot k, and there is a third relation for a scalar product, p dot p prime is actually the same as m square plus k dot k prime, can be proven in a similar way. So therefore, we can express our result in terms of those scalar products, and not all scalar products are independent, and therefore the only independent scalar products can be chosen to be, for example, p dot k prime, and k dot k prime. And then we must be able to express our result in terms of those three variables, as an example. And so we can, in our calculation, in our simplification strategy, we can aim for eliminating everything except for example, 3 selected variables out of those independent scalar products. So, having this in mind, let me present you some highlights of the calculation for unpolarized fermions. So what we need to do is to do the sum over lambda and lambda prime, and also the sum over the spins s and s prime for the incoming and outgoing electron of the squared TFI matrix element. And so that is this mu nu time contracted with the metric tensors, first of all. That comes from the photons. And then we square, so we get E times Q to the fourth power. And for the spinors U and U prime, we use Casimir's trick again. And the spin summation then gives us, first of all, a trace. And then for U, we get P slash plus M for the electron incoming momentum. And for the spinor U prime, we get P prime slash plus M also from the spin summation. And so overall, we get the following trace. Let's say we call it gamma bar mu nu times P slash prime plus M times gamma mu nu P slash plus M. Okay. And where this gamma mu nu is simply this object here. This is, let's call it gamma mu nu. This is a gamma matrix kind of structure. And gamma bar mu nu is defined as basically the Barth version. So gamma dagger mu nu multiplied from the left and right with gamma 0. And if you look at this, then here in this particular case, this just corresponds to the original gamma with the order of gamma matrices exchanged or reversed. So it's just the same product of gamma matrices, but in the reverse order. This happens if you dagger it and multiply with gamma mu, because the dagger operation of one gamma matrix gives the same gamma matrix, but of course because of the dagger, the order of all matrices is reversed. So in this particular case, it just corresponds to the opposite order of the gamma matrices. So in principle, you know here what you have here. So the gamma mu nu, the square bracket, is sum of combinations of products of 3 gamma matrices. So therefore we have here 3 gamma matrix times a gamma matrix, 3 gamma matrix, 1 gamma matrix. So overall we have 8 gamma matrices in the product, and we need to take the trace of these 8 gamma matrices. And of course it's a sum of many terms with different numbers of gamma matrices, but up to 8. And so you saw that there is a recursion formula. The more gamma matrices we have in the trace, the more terms we get in the final result, and therefore we will get very, very many terms if we just blindly evaluate this, but that is what we could do in principle, and so that is in the end what you have to do. But you can try to optimize your calculational procedure in order to minimize the steps that you have to take, but in the end it is a more complicated calculation than the one for the other process that we had, E plus E minus 2 mu plus mu minus, where there were only traces with 4 gamma matrices. So here it's much more involved. And maybe, I don't know whether this is of help to you, but just as an overview, I did this of course several times in my life, this calculation, but maybe the last time I did it completely was order of 10 years ago. And so last week I did it once again from scratch, and it took maybe 6 hours or so. So that is the amount of time that you can expect. And okay, so, and of course you should do it yourself, and maybe you need 7 hours or so, but then it's a good practice to do it. And I will just give you some highlights in order to organize it. Let's say the trace can now be written according to the denominators, because this gamma here, the square bracket, contains 2 terms, and the terms have different denominators. One term has the 2 p dot k in the denominator. The other one has p dot k prime in the denominator, and we will sort according to the denominators. So there will be one term with 2 p dot k square in the denominator, one term with 2 p dot k, 2 p dot k prime in the denominator, and one term with 2 p dot k prime square in the denominator. That is the structure. And then let's just say this is trace 1, the first trace, minus the second trace and the third trace, and plus the fourth trace, and y minus, because the p dot k prime appears here with a minus in the denominator, and here the minus is squared. And so then we have organized it, and we would have to evaluate all those four terms, let's say step by step. And of course, the fourth term comes from the square of this, the first term comes from the square of that, and the term 2 and 3 are the two mixed terms from this sum here in the square bracket. And so the last term, the square of that, is basically the same as the square of the first term, just by replacing the variables accordingly. So therefore, we can immediately see that the fourth trace is equal to the first trace with the following replacement, namely we simply replace k by minus k prime. That's the only difference.
طيب لماذا يمكن أن نسأل سؤال؟ لماذا هذه التفاعلات معقدة؟ يعني نحن راجعنا تفاعل كومبتون وجدناها سهلة جدا، يعني حتى في الانبولورايزد وفي البولورايزد. هنا نجد حدود كثيرة. ما الذي يجعل هذه الحدود كثيرة؟ إذا صدق ظني فإن ذلك راجع إلى كتاب الحلقة 54 والذي ذكرت فيه أن الخواص المغناطيسية تلعب دورا كبيرا في التفاعلات دون الذرية، أو عند الأبعاد الصغيرة. عند الأبعاد الصغيرة فإن التفاعلات، فإن الخواص المغناطيسية تلعب دورا كبيرا. ونحن نعلم أن الخواص المغناطيسية أو أن المغناطيس، المجال المغناطيسي هو مجال موجه ويأخذ شكل دوائر حول في الفضاء، وهذا يشبه تماما الفضاء الذي ذهبت إليه، أنه مقسم إلى مدارات. يعني الفضاء عند الأبعاد الصغيرة جدا فإنه مقسم إلى مدارات. هذا التقسيم المداري للفضاء يجعل أي كونفيجريشن بالنسبة للقوة لا تصلح كثيرا إلا في حالة التي تأخذ نفس شكل الفضاء وهو المجال المغناطيسي. وبالتالي أعتقد أن المجال المغناطيسي يلعب دورا كبيرا في هذا الأمر، خصوصا أن الإلكترون مشحون، بيد أن الفوتون في الكومبتون سكاترينج ليس مشحونا، بالرغم أن الفوتون يتفاعل بالقوة الكهرومغناطيسية، وهذا أمر في غاية الأهمية. إذن هذه التريسيس تخبرنا بأن الإلكترونات أو المجال المغناطيسي يلعب دورا كبيرا، خصوصا أن هذا التفاعل بين إلكترون وإلكترون وليس إلكترون بوزيترون. هذا التفاعل بين إلكترون وإلكترون كما رأينا في الذرة، فإن السبين يلعب دورا كبيرا جدا في تفاعلات إلكترون وإلكترون، أو عندما تجلس الإلكترونات في الذرة في مستوى الطاقة يجب أن يكون السبين مختلف. إذا رأينا هذه الآلية أن السبين يكون مختلف، هذا يأتينا أن المجال المغناطيسي يقوي بعضه البعض، أقصد ينفر بعضه البعض، لأن الإلكترون ليفت هاندد على ما أعتقد، وبالتالي إذا وضعنا أيدينا ليفت هاندد وليفت هاندد مع بعض في سبين في اتجاه واحد، يعطي أن المجال المغناطيسي يقوي بعضه البعض، وبالتالي يحصل تفاعل إلكترون إلكترون، وهذا ما يرفضه الفضاء صناعي الأبعاد. لهذا يجب أن يكون يعني حسب قاعدة اليد اليسرى ليمان يا ربي، قاعدة اليد اليسرى، بحيث أن نجعل الإبهام موجه إلى اتجاه التيار، والمجال المغناطيسي يكون مجموع اتجاه باقية الأصابع المجال المغناطيسي. فهذا يعطينا ماذا؟ هذا يعطينا أن إذا أصبح المجال المغناطيسي في نفس الاتجاه بالنسبة للإلكترون والإلكترون، فهذا يحصل تفاعل بينهما ويحصل قوة شد بينهما، لأنه المجال المغناطيسي يقوي بعضه البعض. وإذا اختلف المجال المغناطيسي بين الإلكترون والإلكترون، فهذا يعني أن الإلكترونان لن يتقاربا كثيرا، ولن يحصل بينهما تفاعل أو شد مغناطيسي أو شد وهذا يعني أنهما يستطيعان يمكثان في مستوى طاقة واحد. هذه فرضية ربما تحقق مبدأ باولي للاستبعاد، لكن محتاج إلى كثير من التمحيص وكثير من التدقيق. في الأيام القادمة إن شاء الله بعد نشر كتابي سأحاول أن أمحص وأدقق في هذه المعلومة. إذا كانت صحيحة فمن الله وله الحمد والشكر، وإذا كانت خاطئة فإنني اجتهدت وأخطأت، وإن شاء الله بقية الكتب سأصحح هذه الخطأ، وسأود يعني سأبحث عن المعلومة الصحيحة ولا أبحث عن هذا الحقيقة بإذن الله تعالى. تعال نواصل.
And on the other hand, this trace 2 and trace 3, they are equal because they are a symmetric combination of both variables. Okay, then let me give you some details of the calculation. So this trace 1, the first trace, which comes from the square basically of the first term in the square bracket, is the following trace. So it's trace, let us start with this. So I need to write down this term here, once with this order and once with the reverse order. So let's start with the reversed order, and then gamma mu is at the very left. Gamma mu is at the very left, then QA slash plus M, then gamma nu, then the spinor sum P slash plus M times then the same term with the correct order of indices, gamma nu times QA slash plus M gamma mu and P slash plus M. So this kind of trace with 8 gamma matrices, 1, 2, 3, 4, 5, 6, 7, 8. And of course, also terms with masses and so on. So what can you do? One thing that you can do before you simply blindly evaluate the trace is to look at such a combination here. Here you have a combination which I want to highlight, gamma nu P slash plus M gamma nu contracted over nu. So somehow there must be a simplification where you contract over nu. Afterwards the nu doesn't exist anymore, it's a summation index. And so let us look together what happens if you just calculate this single combination here. Gamma nu P slash prime plus M gamma nu. How can you simplify this expression? We can simplify it by using the anti-commutator of gamma nu and other gamma matrices. So we have here a simple term, M times gamma nu, and a more complicated term, gamma nu P slash prime gamma nu. Now here in the simple term, gamma nu is directly contracted, and so this term is the same as if I write nu in this way. Then you see the term is the same as the one where the gamma matrices have the opposite order. So you can replace the two gammas by their anti-commutator, but the anti-commutator is a metric tensor, and so this is the same as M times metric tensor G nu contracted over nu. And so this is now a number which is 4. 4 times N. Times the unit matrix, of course. So that is simple. So here gamma nu contracted like this just gives the number 4. In the more complicated term, we use the anti-commutator and we write this gamma nu as minus the opposite order plus 2 times P prime nu times gamma nu. Okay? So we use the anti-commutator. The anti-commutator is 2 P prime nu, and then we can replace this by the opposite order plus the anti-commutator. This is a correct replacement. And now what happens? So here in this term, gamma nu is directly next to each other, so we get again the number 4. so minus 4 p prime slash. And from here, p prime nu contracted with gamma nu is also p slash plus 2 p prime slash. So we can simplify and we get 4m minus 2 p prime slash. So long story short, we have here an initial expression with 3 gamma matrices, product of up to 3, and in the end we have only up to 1 gamma matrix. So we have reduced the number of gamma matrices in our product by 2. Okay? And this is a quite common simplification that you can memorize. So whenever you see such a structure, gamma nu from the left and right, and in between something else, you can always simplify it in such a way. And here this is the result. And actually in the expression that appears several times, so here also if you use cyclicity of the trace, that gamma mu, you can put it here. Then you have here gamma mu something, gamma nu is the same structure. You can simplify that as well. And after doing that simplification and the other one, you have only 4 gamma matrices instead of 8, and the trace becomes really simple. So therefore, then using kind of standard steps, you get the following result. This trace is 32 times m to the 4 plus m square pk plus pk prime times pk. That's just the result. Okay. So you apply as often as you can this sort of idea. And then the result is not so complicated. Similarly, let us look at the second trace. The second trace from the mixed term from here, gamma, we have once this factor times the other one, and one of them appears with the opposite order. This is our trace 2, and so trace 2 is the following trace. Let us start with gamma nu times qb slash plus m times gamma nu, then p slash prime plus m, gamma nu qa slash plus m, gamma mu p slash plus m. So here you see, this is the first term, gamma nu qa and gamma mu, and this here is the second term, but in reversed order, contracted over mu and nu. And in between we have the spin sums of the two spinors, u prime and u. Now if you look at this, that is more complicated than the first trace, because here the contraction over mu and nu is somehow crossed. And so it's not as simple as here. So there the simplification was that you directly have nu, and in between you have only one gamma matrix. So if you now look at the mu contraction, you have 3 gamma matrices in between. So if you want to use that trick, just explain to you, the trick is going to be more complicated. And so let's do however the same trick. So for example here, you start with this and you evaluate the nu contraction with 3 gamma matrices in between. So and if you do that, then the result is the following: minus 2p prime slash k slash gamma mu plus m times 8 qb mu plus 4k mu minus 4 qb mu times p slash prime. So this is the result of that orange contraction. And you see, again, it has simplified because initially we had up to 5 gamma matrices, and here we only have up to 3 gamma matrices. And I simplified as much as possible such that we only have one single simple term with 3 gamma matrices, and all the other ones even have only 1 gamma matrix or even 0 gamma matrices. So it is maximally simplified. And I simplified it also in such a way that in the only term where we have 3 gamma matrices, the gamma mu appears on it the right. So if you now plug that into the full expression, then you see gamma mu is here. Gamma mu, you can again use that rule from before. And then you have even two gamma matrices less, and then you can evaluate the trace quite easily. So therefore, then this trace of this second expression gives the following 16m square times 2m square plus pk minus pk prime. So the result is quite simple after a long calculation. And therefore, if you evaluate everything, we have now indicated the first trace, the second trace. The third is the same as this one, so this just gets multiplied by 2. And the fourth trace is the same as that one, but exchanging k by minus k prime. So here you get minus k prime. And
طيب هنا كما ذكرت سابقا أن التريسس مساوية لبعضها البعض ومعاكسة لبعضها البعض، وهذا ناتج من نوع من السيمتري. هذا السيمتري تفرده الكتلة، هذا السيمتري، هذه هي السيمتريس تفرده الكتلة. الكتلة تحمل في داخلها الاسيمتري اللي هو عدم السيمتري، نقيض السيمتري، عدم السيمتري تحمله الكتلة في داخلها. يعني لا تتكون الكتلة إلا في داخلها عدم تناظر داخل الكتلة. خارج الكتلة الفضاء متناظر، وهذا واضح جليا في الثقب الأسود. نجد أن الفضاء مقلوب داخل الثقب الأسود، وخارج الثقب الأسود الفضاء ليس مقلوبا. قلب هذا الفضاء يعني عدم السيمتري أو نقيض السيمتري اللي هو يسمى الاسيمتري. إذن بما أن الكتلة تحمل عدم السيمتري، إذن ماذا لو افترضنا أن الفضاء أصلا ليس سيمتريا، يعني هو ليس متناظرا. وهذا واضح في الفضاء ثنائي الأبعاد أنه ليس متناظرا. الكتلة تحمل هذا التناظر داخله، وبالتالي تجعل الفضاء متناظر في الخارج. طيب هذا يعني أننا عند الأبعاد الصغيرة، إذا افترضنا أن عند الأبعاد الصغيرة هنالك عدم تناظر كبير عند الأبعاد الصغيرة، فهذا عدم التناظر يظهر جليا في هذه التريسس. ماذا إذا كان التريس الأول يساوي الرابع والثاني لا يساوي الثالث؟ هذا ما يحصل في الفضاء الصغير جدا عند التفاعلات، خصوصا عند التفاعلات. التريسس غير متساوية تظهر الكتل من أجل أن تجعل التريسس متساوية، وهذا ما يخلق الكتل. كلما زاد عدم التناظر في الفضاء الصغير كلما خلقت كتل أكبر. هذا ما أنظر إليه أنا في هذا الموضوع، وهذا ما سيقوم عليه كتابي القادم، الحلقة 54 بمشيئة الله.
Here, that gets a minus sign. That's all. And so therefore we obtain the following full result. It's the following 32 e times q to the fourth power divided by 4. So that is the natural prefactor which you obtain because all the denominators have a factor 4. From here, this is the factor 4 from the denominators, and the factor 32 arises from the numerator calculation. Here 32, that appears twice. You also get 32, so I factor that out. And then times the following. m to the 4 plus m square pk plus pk prime divided by pk square. That is our first term with the first denominator squared. And you see this comes directly from here. Then plus m to the 4 minus m square pk prime plus pk prime divided by pk prime square. This is the same where I replace k by k prime. And then the mixed term, m square times pk prime in the denominator and 2m square plus pk minus pk prime in the numerator. This is the result of the calculation of the spin-summed squared matrix element. Let us discuss it. The result here actually is famous. Obviously, Compton scattering is extremely important. And so the first calculation was done by Klein and Nishina. So the result is called the Klein-Nishina formula. And we will now give a small discussion of the result. So this result is correct, and it is Lorentz invariant, as you can see. It depends only on those scalar products, and the Klein-Nishina formula uses this result and goes into a specific frame which is useful for the interpretation, and that is the rest frame of the initial electron. So let us go into the rest frame of the initial state electron, where the initial state electron momentum 4 vector is just the rest mass and 0 for the spatial momenta. And let's give some kinematics for all the momenta. So the initial photon momentum k is now called like this. Okay. So the typical name for the energy of the photon is omega. So we would start with an omega photon, and that corresponds, of course, to the classical case where we have an electromagnetic wave with frequency omega. So we can make contact to that. And the outgoing photon has energy omega prime, and it has some direction, let's say sine theta times omega prime 0 cosine theta times omega prime. In other words, the final state photon has an angle theta compared to the initial state photon, and the initial state photon happens to come along the z direction. And the outgoing electron, p prime, is just given by momentum conservation, p plus k minus k prime, and so I do not write down the explicit components. They are defined by momentum conservation in 4 dimensions. Okay, then we have those important scalar products which appear in the result, which are now p dot k. What is p dot k? P dot k is just m times omega. P dot k is just m times omega. What else do we need? P dot k prime. What is p dot k prime? P dot k prime is just m times omega prime. M times omega prime. Then what else do we need? K dot k prime. K dot k prime is the scalar product of the two k's here, and that is omega times omega prime times omega times omega prime times 1 minus cosine theta. Although this k dot k prime actually doesn't even appear in the formula for the final result, but let's nevertheless write it down. And let's also write down some relationship which is important. Namely, you can write down 0 is equal to k prime square. So the outgoing photon is massless, of course, therefore the momentum k prime satisfies k prime square is 0. But what does that mean? You can write k prime times by momentum conservation. K prime is the same as p plus k minus p prime. And then you get k prime dot p is equal to m times omega prime. K times k prime is so k prime times p is that minus k prime times p prime is m times omega, and k times k prime is plus omega prime times 1 minus cosine theta. And so that means you have a relationship between omega prime, omega, and cosine theta. And so now you can solve for the frequency of the outgoing photon, omega prime, in terms of the scattering angle theta. And so this gives us the very important frequency shift of Compton scattering, because as we said, if we are not in classical physics, the frequency is not the same as in the initial state, but the frequency is different, and how much different is given by this formula. So therefore, we get omega prime is equal to omega. We just solve for omega prime. It's a linear dependence on omega prime. Omega divided by 1 plus omega over m times 1 minus cosine theta. So that is the general relationship. And so you see that there is a limit where the quantum mechanics doesn't play a role. If omega is much smaller than m, so the frequency is small compared to the rest mass, then you can forget about the correction term and you get omega prime is approximately equal to omega. That is the limit in which you can apply classical electrodynamics. But if this omega is similar to the rest mass of the electron or even bigger, or at least where this factor is relevant, you get a frequency shift, which is a quantum mechanical effect. So an equivalent relationship which is useful in the calculation is 1 over omega prime is equal to 1 over omega plus 1 over m times 1 minus cosine theta. So this is something that you can sometimes plug into your formulas. Okay, then in the result, this curly bracket can now be simplified. All the scalar products are given in terms of m times omega prime, so on. So we can replace everything here by that simple result. And then what do we get? So from the first bracket, for example, in the denominator, we just get omega square. And in the numerator, we get m square plus m omega plus omega prime. Okay. So one factor of m squared can be cancelled, and then what remains is just literally plugging in the scalar products. Basically, whenever you see a k, you replace it by omega. K prime gets replaced by omega prime, and the m's essentially mostly cancelled. So that's this. The second term is then m square minus m omega prime plus omega prime divided by omega prime square. And the third term is minus 2m square plus m omega minus omega prime divided by omega times omega prime. Okay, and if you simplify it, then you see that you here, for example, the m square term, m square times 1 over omega square plus 1 over omega prime square minus 2 over omega times omega prime. So this looks like a binomial formula. So this is exactly this difference, 1 over omega prime minus 1 over omega overall squared. So you can replace that by this 1 minus cosine theta. And so then all the m square terms are completely simplified and give basically 1 minus cosine theta squared. And so the other terms can also be simplified, and after a small number of steps, you get omega prime divided by omega plus omega divided by omega prime minus sine square theta. So that is a trivial replacement here. So, but then you have a very simple result for the curly brackets. And we can write down the full result of the Klein-Nishina formula. So there is now a result for the differential cross-section, d sigma by d omega. And remember that here in this lecture I do not really teach you all the prefactors of such cross-sections. They are from particle physics, but that is not the point here. The result is e q to the fourth power divided by 32 pi square times m square times omega prime divided by omega square. And all of this factor you cannot quite understand. At least we didn't derive it. That is from phase space. And the definition of what cross-sections are. And what you can understand, because we discussed it already, is first of all the unit. The unit of a cross-section is 1 over energy square, and you see it here. It's 1 of the mass square of the electron. And then we have a phase space factor from the final state momentum divided by the initial state momentum. We had the same factor also in the previous calculation of the other process. And this factor is small if the final state momentum is much smaller than the initial state momentum, but the factor goes to unity if the final state and initial state momentum are similar. So this can be understood intuitively, but the prediction from QED is the factor which comes now, and that is exactly the factor that we have here, namely omega prime divided by omega plus omega divided by omega prime minus sine square theta. That is the QED prediction. And this here is, of course, the Klein-Nishina formula. It is the cross-section for, or in other words, the probability for Compton scattering in certain angles, averaged or over all the spins of the initial and final state particles. So, and in the beginning of the chapter on Compton scattering, we argued that there is a classical situation with Thomson scattering, which we should be able to understand in classical electrodynamics. There is an ultra-relativistic limit and something in between, and QED provides a unified description, and this is the unified description. It is valid for all energies, specific to the rest frame, but nevertheless it's valid for all energies of the initial state photon and the final state photon as well. So therefore, let us look at some limits, and the first limit is the classical limit, or non-relativistic. So in the classical limit, we have that the rest mass of the electron is much heavier than all the other energies in the process. Therefore, in particular, the photon energy is much smaller than the rest mass of the electron. And so the electron will remain non-relativistic in the process, and we can neglect the quantum mechanical nature of the photons, except for the fact that we consider just one photon. But in this limit, as we already saw, omega prime is approximately equal to omega, so there is no frequency shift from the explicit calculation. And in that case, the cross-section d sigma by d omega becomes the following. So the factor omega prime over omega is now 1. And in the square bracket, all the fractions are also 1, so we have 2 minus sine square theta. 2 minus sine square theta times the prefactor e times q to the fourth power divided by 32 pi square times the rest mass square, and then times 2 minus sine square, or that is the same as 1 plus cosine square theta. And this result is a well-known formula that we have listed the last time, namely this is the cross-section that you derive in classical electrodynamics for this Thomson scattering just by looking at the classical accelerated charge moving in the incoming plane wave with a frequency omega. So that agrees with the classical limit. So this is the Thomson cross-section. In classical electrodynamics. So our QED prediction reproduces the result from classical electrodynamics in the appropriate limit. There are no corrections in the precise limit, but of course, if the omega over m becomes non-zero, there are corrections which are calculable. Now at this point, I want to interject a small discussion on something which is quite important also for, let's say, further discussions of QED, namely the definition of the electric charge. What do we actually mean when we say a particle has charge whatever? How do we define it, and both in theory and in experiment? And ultimately, in physics, you should really provide operational definitions of the observables. In other words, you should, even as a theorist, tell the experimentalist, this is the procedure you should do in your experiment, and this is the way to extract the number. And then by that procedure, you obtain, for example, the number which corresponds to the electron charge or the muon charge or to something else. And so here in the context of QED, we have an important parameter, E and Q. Q is by definition an integer minus 1, but E is a real number. It is the elementary charge. And so the question is, what is the operational definition of E? How should an experimentalist determine the value of E? And so here we have now the opportunity to write down an explicit operational definition of the measurement of the electric elementary charge. And this definition I'm going to write down is the one which is really used in the literature. In full QED, also including higher order effects and so on, and we can understand it here. So we are looking for an operational definition. And the definition is as follows, namely measure Thomson scattering in the appropriate limit in the classical limit. So if you want to measure the elementary charge, you take an electron and shoot an ultra low energy photon onto it and measure the cross section in that limit here. And then we say, by definition, the result is this formula here. So the experimentalists measure some cross-section strength, some value. They map it onto this formula, and by mapping their experimental measurement onto the formula, assuming the electron mass is already known, they get the value of E. So this defines, since we have Q equal to minus 1, a quantity which we can call E in the Thomson limit. So then you get an experimental value for the elementary charge, which you might call E in the Thomson limit, and you have it defined in an operational way. And so then there is, of course, a value. If you do that procedure, then you get alpha, which is equal to E in this Thomson limit square divided by 4 pi. This alpha is then approximately 1 over 137 with a few digits which are very precisely known. Why is it so important to have an operational definition? Because suppose you now have some hypothetical new theory. Somebody has a new theory, and that new theory predicts something for Thomson scattering. Let us suppose some hypothetical theory predicts here some factor 1 plus delta in your new theory beyond the standard model physics theory. Let's say your new theory predicts a correction here. Then you know the experimentalist has done what I wrote here, and you read the number for the electric charge is this value. But you know exactly what the experimentalist has done in order to extract the value from experiment. So you know that in your theory with a modified formula, you cannot plug in the same value in your electric charge as the one coming from experiment, but you must correct it by your new prediction. So you always have to now calculate in your theory your prediction for the cross-section in terms of your theory parameters and your theory relationships, and to map it to the same experiment, and then you might discover that actually the parameter E which appears in your theory does not mean the same thing as the E in the Thomson limit which comes from experiment. And so this is an important thing. But we have shown that in QED, at least in lowest order perturbation theory, the prediction of QED is exactly that, and therefore at lowest order in QED, the elementary charge which must be put at this position here is exactly the one coming from experiment with this numerical value. But this kind of logic needs to be applied in all observables, and so there are often, at least it's kind of possible, to have misunderstandings, and therefore it's good to be precise about how quantities which enter theory predictions, how the quantities are actually defined experimentally. This is a discussion which becomes more prominent also in the context of renormalization. But it's already possible to make the point here. Okay, now that was the low energy limit. Let us therefore now come to the high energy limit. For the high energy limit of Compton scattering. Oh, okay. Like at tree level you need 6 hours, and at the next order you need 5 hours. Is that sort of your question? Or 4 hours?
If the problem going to higher order is just higher the diagram, or is calculating
I mean, at the one loop level, the procedure consists of calculating the extra Feynman diagrams. But the calculation of them is quite a bit more complicated than the tree-level Feynman diagrams, and therefore the answer is kind of mixed. So yes, it is only calculating the additional Feynman diagrams. That's really what you have to do. But in order to calculate them correctly, you need to go through the procedure and the discussion of renormalization, because at the one-loop order, there are these so-called divergences in the calculation of the Feynman diagrams. Then you need to deal with those divergences. You need to develop an understanding and theory of renormalization. But once you do that, then of course it is a matter of investing some effort in order to calculate the higher order corrections, and then you would derive, for example, at the top line here, some well-defined correction factors to the Klein-Nishina formula. And actually this discussion here should then be repeated And but I do not want to say too much because it's a little bit convoluted, so it would be nicer to explain it with the formulas available. But what happens is that in the general case, of course, there are correction factors from higher orders and so on, but surprisingly, if you go to this classical limit, all the corrections go to zero. So somehow, magically, this result here is an exact result. It's not only true in lowest order perturbation theory, but it's true in all orders. It's an exactly true statement for this cross-section in the classical limit. So, and this is not, let's say, true in other processes, but in this particular process, it is really true that the classical result from classical electrodynamics is reproduced exactly, even if you take into account all the infinitely many Feynman diagrams which contribute to Compton scattering. So that formula will remain exactly valid. And that explains also why this operational definition is so useful, because if we say experimentalists measure the cross-section and match it to that formula, then you know the formula is exactly true in QED. Therefore, if that is the result, the number for the Thomson limit charge, you know that in QED this is the exactly correct charge you need to put into all QED predictions that you ever want to calculate, also for all other processes. And so that makes this operational definition very powerful. And that is a theorem that all the higher order corrections to this formula vanish, and we cannot intuitively understand why the theorem holds at this point. We should have to investigate a little bit more in detail what kind of higher order corrections there are and how they should behave. Yeah, you need to, let's say, apply maybe a correction factor. Maybe you need to apply a correction factor, and then the charge in your theory has a different value than the measured charge, just because your formula is different. So of course your theory, if your theory contains that factor here, 1 plus delta, or let's say simply put, times 2, okay, your theory predicts that, the factor 2. Then of course your theory must also reproduce experiment in Compton scattering. So then in your theory, let's say your theory square times 2 must be the same as the Thomson limit from experiment square in order to match your theory to the same experimental observation. And then once you know that, you can derive predictions in your theory as a function of your theory parameter. And the predictions will be whatever your theory predicts, but you have to match, first of all, your theory to experiment as well. I mean, you don't know whether your theory is a correct theory of nature, describing nature correctly, but you can, for one particular observable, you require your theory prediction agrees with experiment, and so you adjust the theory input parameter such that you agree in one particular case with one observable. And then you derive theory predictions for all other observables and you compare again to experiment. And if your theory describes nature correctly, it will agree with all observables. And if your theory is wrong, then it might agree with one observable by construction, but all other observables are predicted incorrectly. Now there is another question. So basically, this discussion here means that all the low energy determinations of the electric charge where classical electrodynamics is relevant are now basically equivalent. Atomic physics, low energy Thomson scattering, all other measurements where the electric charge behaves basically classically behave in this way, and so they should be equivalent. But if you measure the electric charge in some high energetic experiments where quantum field theory effects are relevant, then that would not be equivalent. And so, for example, one very obvious way to also define electric charge would of course be this process, E plus E minus, 2 mu plus mu minus. For example, at 100 giga electron volts energy, very, very high energy, so that all particles are ultra-relativistic. We know that our cross-section is basically given again by the electric charge to the fourth power times some factor, maybe divided by the center of mass energy squared times some factor, let's say, times some factor f. So then you have a prediction, and you could also say, experimentalist, measure the cross-section of this process at 100 GeV energy, and by definition I say this cross-section theory prediction agrees with experimental measurements at 100 GeV energy, and by this equality I determine the numerical value of the electric charge parameter E in my theory. Then I will get some number. The question is whether I get the same number as here. If I get the same number, then the theory consistently describes, of course, all experiments. If I get a different number, it means my theory cannot consistently describe all experiments simultaneously, and therefore the theory is wrong or not sufficient to describe nature correctly. Right. And so here, for example, this process does not have this property that all higher order corrections vanish. Here the higher order corrections are actually important. And so actually I wanted to discuss sort of things like that next week. Maybe we'll do it in a little bit more detail, but since you are asking, maybe let's do it in a little bit more systematic way. Just as a small outlook discussion, say basically any theory contains some input parameters, and to make our life simple, let's assume QED has only one input parameter, let's say the charge E. Let's forget about the electron mass. There is one input parameter. That means in your theory you can predict from the input parameter E, you predict many observables. Observables sigma 1 is a function of E. Observable sigma 2 is another function of E. Observable sigma 3 is another function of E. And what I mean by this would be the cross-section for Compton scattering. This would be the cross-section for E plus E minus at 100 GeV energy. This would be maybe this process at 1 GeV energy, very slow energy, and so on. So you have, and Compton scattering, of course, also exists at in the classical limit at very low energies, and Compton scattering also exists at very high energies, let's say 100 GeV. And then we have basically, of course, infinitely many, but let's say 4 different observables, which are all predicted by theory. And each observable gets a theory prediction, which is a function of E. And we have now evaluated these functions here at lowest order, but of course there would be higher order corrections also, except for in this case where somehow the higher order corrections are 0, but in principle everywhere there is a power series in E, perturbative series, and we have many, many different theory predictions. And then on the other hand, in experiment, we of course have observables. We have sigma 1 from experiment, sigma 2 from experiment, sigma 3 from experiment, and sigma 4 from experiment. And now what you can do is you can select, for example, one observable, and we have now concretely selected this observable where we say at first I require that this observable by definition agrees with the experimental value. By requiring this equality for just this observable, I get a numerical value for E. Then this E is experimentally defined via this observable. So E experiment. And then I plug in this E, and so then I can now concretely predict numerical values for all the other cross-sections by plugging in the measured E measured in this process. And so then I can ask, does now my theory prediction for the second observable with this input value agree with experiment? Does it agree for the third observable? Does it agree for the fourth observable? And so on. And if all of them agree with all experimental values, my theory is validated. But if somewhere there is a discrepancy, then of course I falsified my theory. That is the logic. And of course I could now select also a different process to measure my input parameter. I could select, for example, observable number 4, and experimentalist measures it. Theorist calculates this formula, and then by matching sigma 4 between theory and experiment, I also obtain a theory experimental value for this charge, and then I can predict those 3 observables. But always, in principle, I need to select, or at least in a simplified picture, of course, you select one observable, you match theory to experiment, extract the input parameter, and then you have infinitely many predictions of your theory which allow tests and validations of the theory. That is the point. And so in the literature, there are different definitions of the electric charge, and different values of alpha. For example, you often see value alpha is 1 over 128 and so on. In contrast to that value here, so this is 6% difference, so quite a big difference. And that does not mean that the theory is inconsistent, but that means that you have chosen a different definition. So this alpha does really not mean the same as that one, and so often it's called alpha hat or so. So it's just a different fine structure constant, which is defined in a different way. And so there would now be a theory prediction. QED would, for example, predict that this alpha with some operational definition, say this alpha is given by the other alpha plus some prefactor times alpha square plus alpha cube and so on. So you get a prediction from theory for the relationship between the 2 different alphas. So they basically correspond to 2 different observables, and there is a relationship between the 2, and that again can be tested experimentally. So therefore, this is a different discussion. So there are different definitions for fine structure constants in the literature, and also for other quantities which are important, because it's not the only convenient way to define charges in that way. Okay. So I would like to probably come back to this discussion a little bit next week, where I want to discuss renormalization a little bit. But if you want to know more right now, let me know. But this is kind of the logic of input parameters versus output. Okay, now we have lost a lot of time, but maybe it was worth it. But I wanted to discuss actually the high energy limit and then start a new topic, but maybe this will not be possible. Let's see. So very few words about the high energy limit. Which is of course your exercise. And here we look at the following situation. we go to the center of mass frame where the electron is moving, and the electron and the photon, they collide head on, and they both have a very high energy such that the electron is relativistic and the photon has the same energy as the electron. So we have the following kinematics: P is equal to E0, 0, E. K has the same energy, 0, 0, minus E, such that the spatial momenta add up to 0. And P prime, the outgoing electron now, P prime, has an angle theta, E sine theta times E, 0 cosine theta times E. And we neglect the mass, m goes to 0, and then our scalar product P dot k is simply equal to 2 times E square. Here P dot k is 2 times E square, and the other scalar product P dot k prime is E square times 1 plus cosine theta. Okay, then our main result, which was this curly bracket, now gives us the following. The sum over all the spins of our squared matrix element is 32 E times Q to the 4th power divided by 4 times 1 plus cosine theta divided by 2 plus 2 over 1 plus cosine theta. Okay, so you see the curly bracket that we had before. Those terms which are suppressed by the mass, they are now neglected. And the terms which are not suppressed by the masses, they all have the same energy dependence, so the energy drops out completely. The result is dimensionless, so the energy has completely dropped out. And then we have those terms with omega square in the denominator, and the term with omega over omega prime or omega prime over omega, so that corresponds to those two terms here. Basically this divided by that and the opposite. So, and now we see here, and that is what I briefly want to discuss, that there is a singularity, and a little bit telling you the solution to the exercise. The singularity happens for theta going to pi, 180-degree scattering, because for theta equal to pi, the 1 plus cosine theta here goes to 0, and we have 1 divided by 0 in the second term here of our result. So what is the kinematic situation of this singularity? Theta is equal to pi. That means kinematically the process looks like this. The electron comes in, the photon also comes in from the opposite side, and then theta is 180 degrees, so therefore the electron basically is backscattered in the opposite direction, and the photon also is backscattered in the opposite direction. So maybe you can look here, a very small angle chi, which is approximately 0. So you can say the angle theta is equal to pi minus chi, and chi is very small. And in this particular case, the cross-section d sigma by d omega is essentially given by the singularity 1 plus cosine theta. If theta is pi minus chi, then this is the 1 drops out and we get chi square over 2. So it's basically 1 over the angle chi square. Okay. So we have a singularity of the cross-section for this kinematic situation, where the cross-section behaves like 1 over chi square, and chi is a very, very small angle, the difference between 180 degrees and the angle theta. So
طبعا نظريتي بموضوع السنجلاريتي لديها حل، والحل هو معروف ونردده دائما أن الفضاء ثنائي الأبعاد يمنع هذه السنجلاريتي، يمنع هذه السنجلاريتي بشتى الأنواع، لأن السنجلاريتي تمثل طاقة عالية جدا مثل الثقب الأسود. فالفضاء ثنائي الأبعاد يمنع هذه السنجلاريتي بحيث أنه يختار الزاوية بنفسه، لا يجعل زاوية تساوي زيرو، أو هناك آلية معينة يمنع هذه السنجلاريتي بها، بحيث أنه يضيف حدود أخرى للمعادلة، بحيث أنه عندما نشتغل عليها تجريبيا لا نجد هذه السنجلاريتي حتى لو كانت الزاوية بينهما 180 درجة. وهذا مفترض أن نستكشفه في كتاب القادم الحلقة 54 للعلماء الذين يعني استهوتهم موضوع المجال المغناطيسي الذي يعمل كقوة قوة نووية قوية strong field strong force. تخيل أن المجال المغناطيسي يشتغل مثل الجلوونات، المجال المغناطيسي يشتغل مثل الجلوونز، فبدل ما نقول هناك جلوونز نقول هناك مجال مغناطيسي. طبعا هذا أمر في غاية الغرابة، والمفترض أن يستهوي كثير من الناس، فإننا نتعامل مع الجلوونز مثل المغناطيس الذي بين أيدينا. إذا تقارب مغناطيسان مع بعض فإن القوة بينهما تزيد، وإذا تباعدا القوة تضاعف، لكن هنالك في ذلك الفضاء الوضع يختلف، إذا تقاربوا الوضع الفضاء القوة تزيد، وإذا تباعدوا أيضا القوة تزيد، وهذا بسبب المتر وأنتي متر في الكوارك التي لها إذبين، هذا إذبين 1 هذا إذبين 0 إذبين 1، وهذا إذبين أقصد إذبين أب وهذا إذبين داون، وبالتالي هذا الإذبين يجعل المجال المغناطيسي يقوي بعضه البعض وفي ذلك الفضاء ضيق، وعندما نحاول أن نستبعد الكواركات مع بعض هذا المجال يقوى. بالتالي مفترض أن نظريتي تطبق الكونفاينمنت أو الفريدم سيمتوتيك فريدم. فالمجال المغناطيسي يلعب دورا محوريا في تصادم في المفاعلات أو مصادم الجزيئات الكبير أو مصادم الجزيئات عموما أو فيزياء الطاقات العليا. ومجال الكهربائي أيضا يلعب دور لكن ليس كبيرا جدا. طيب ماذا عن المجال التصاغلي؟ المجال التصاغلي أصلا تم محاربته بين الفضاء ثنائي الأبعاد، يعني الفضاء ثنائي الأبعاد أول من يحارب المجال التصاغلي، لهذا يعطي فرصة للمجال المغناطيسي أن يستفحل. وربما أن الفضاء ثنائي الأبعاد هو الذي يجعل المجال المغناطيسي يستفحل، أو كمشكلة كعيب فيه أن المجال المغناطيسي يستفحل، لأن المجال المغناطيسي سيعمل هنا عكس الفضاء ثنائي الأبعاد، والقوة السترونج فيلد والويك فيلد تندمجان مع بعض وتصبحان معاكسة تماما للفضاء ثنائي الأبعاد، يعني شيء من هذا القبيل. لكن ما أقول أنه سنجلاريتي محالة في جميع الأحوال، سنجلاريتي محالة في جميع الأحوال.
How can we discuss this? That is your job in the exercise at chi equals 0. First of all, angular momentum conservation requires something. Namely, what does angular momentum conservation require? You see, now let's assume the angle is exactly pi. Then we have here exactly backscattering. And so then, of course, our initial state is an eigenstate of angular momentum in z direction. The final state is also an eigenstate of angular momentum in z direction. So angular momentum conservation means that the initial and final state must have the same angular momentum. And that is only possible if the angular momentum here plus minus 1/2 adds up to 0, and here plus minus 1 adds up to 0 as well. So therefore angular momentum conservation is only possible if the initial state spin of the electron plus minus 1/2 and the outgoing spin minus plus 1/2 are opposite to each other, and for the photon it's the same. So S must be equal to plus S prime, and lambda must be equal to plus lambda prime for the incoming and outgoing photon, which just means that the total Jz is conserved. However, that is not all, and there is more to it, and the more comes from the exercise. Namely, the detailed study of the Feynman diagram reveals more. Look at the Feynman diagram with the singularity. One of the two Feynman diagrams has the singularity, and this shows if lambda is equal to plus 1, then the outgoing spin or helicity of the outgoing electron must be plus 1/2 as well. So there is a correlation between the incoming photon helicity and the outgoing electron helicity, which you cannot simply obtain from angular momentum conservation. So this must hold for the singularity. So this enhanced part of the cross-section, the one which goes like 1/chi², which blows up in the 180-degree limit, this part of the cross-section is only possible for this particular spin or helicity configuration. And that is interesting because it also gives an useful technical possibility. Namely, you can now polarize electrons. You know, you have initially a polarized photon, and in the final state you have a polarized electron with known helicity. And maybe you want such a polarized electron beam, and if you are able to have a polarized laser beam, for example, then you are now able to polarize an electron beam in this way. So that is interesting. So let's say you have a polarized laser, and in this way you can get a polarized electron beam. So that is the outcome of the exercise, and that is why this is interesting, and we will discuss it, of course, on Thursday in the exercise after you have calculated it. Then you see that, so the practical thing that you need to do is you prepare a polarized laser, shoot the laser onto the electron, and then you see that many electrons will be scattered exactly in the direction of the laser beam, and those electrons scattered exactly in this direction, they have this polarization. So that is useful. Okay, that was my last remark to Compton scattering. So now I would like to change the topic and come to a next section. And tomorrow we will continue. So tomorrow is lecture in case to avoid confusion. And the next section of the lecture comes back to gauge invariance, and I want to collect a few remarks which are relevant in that context.
طبعا في موضوع السنجولاريتي أنا ذكرت أشياء أن الفضاء لا يمنع ذلك. من ضمن الأشياء التي يمنعها الفضاء يعني من ضمن التصرفات التي يتصرفها الفضاء هو أن يخلق مزيد من الكتل، مزيد من الكتل، لأنه عدم السيمتري هذا تحمله الكتل، فيخلق مزيد من الكتل تذهب تخلق مزيد من الكتل تطرد من التفاعل. ثانيا ما قالوا عن السبين أعتقد أنه فيه شيء ما أنا خافي عليه، أنه الفضاء منع أو سمح بهذا السبين أيضا لآلية من آليات الدفاع عن النفس، فقط سمح بهذا السبين أن يحصل. الانتراكشن انه السبين للفوتون يساوي 1 والالكترون يجب ان يساوي نص. ربما يكون شيء من هذا، ضيق الموضوع يعني ضيق التفاعل، بحيث ان لكي يحصل هذا التفاعل يجب ان تطبق شروط، مزيد من الشروط القاسية.
All right, so the next section is the magic of gauge invariance.
طبعا عندما يتحدث عن the magic of gauge invariance، عندما يقول the magic فهذا يعني طوالي مباشرة نذهب إلى نظرية لنعرف التفسير لهذا الماجيك. طبعا الأمر واضح أن الفضاء صناعي الأبعاد يقوم بكل الحسابات ويقوم بكل الإجراءات ويعطيك النتائج التي يعني تمنحه الأفضلية، وبالتالي كما قلت هذا يدخلنا في موضوع unconsciousness، لكنه في الحقيقة ليس consciousness، ما يفعله هو الله، هو ليس الفضاء ذات نفسه. الفضاء ذات نفسه ليس واعيا، لكن ما يفعله هو الله في كل لحظة، في كل single interaction، في كل شيء، في كل هنالك قدرة ربانية، علم رباني، إحاطة ربانية، تفاعل رباني، وتدبير رباني في كل شيء في حياتنا، من أصغر الأبعاد إلى أكبر الأبعاد. ربنا غيور جدا على حدود مملكته، فبالتالي إذا وصلت كل كتلة لا نهائية فإن ربنا سبحانه وتعالى سيتدخل مباشرة وسيمنع ذلك بمفهوم الذي قلته الآن، الفضاء صناعي الأبعاد. لكن إذا اعتبرنا أن هناك consciousness بالنسبة للكون ذات نفسه، ماذا يحدث في الكون إذا إلكترون وفوتون دمرا جزء كبير من الأرض؟ ماذا يحصل؟ ولا أي حاجة. ماذا يحصل للكون ككل إذا الأرض كلها تدمرت؟ لا شيء. إذن يعتبر أن الكون عبارة عن إنسان. طيب إذا أصيب الإنسان ولا قدر الله بغرغرينة وتآكل أصبعه، فما سيفعله هو أنه يبتره. هذا ما يفعل الكون إذا كان واعيا، يبتر الأرض. لكن إذا كان هناك إنسان لله مثل أعلى غيور جدا على يعني مملكته، يعني مثلا إنسان صنع هذا الروبوت، أو مثلا نقول أب لابنه، الابن جاءته هذه الغرغرينة. طيب فماذا يفعل الأب؟ أولا سيبحث عن طريقة لا يقطع إصبع ابنه. إذا وجد هذه الطريقة سيفعلها، واعتبر يعني إذا اعتبر أنه لديه هذه الطريقة فإنه مباشرة سيفعلها، لأنه الابن هذا أحد ممتلكاته، بالرغم من أن الابن ربما يكون لا يعلم هذه الطريقة، وبالتالي هذا يصب طبعا في consciousness، يعني الابن لا يعلم طريقة الحل، فأول علاج يلجأ له هو القطع. لكن الوالد إذا كان يعرف الحل، يعرف هناك دواء يعالج هذا الأمر بسرعة كافية وبطريقة أفضل، فالأب سيعطيه للطفل الابن مباشرة. هذا هو ولله المثل الأعلى، هذا هو ما يصرف الله ربنا سبحانه وتعالى عنده حل لأي مشكلة. وبالتالي إذا حس أو إذا رأى أو إذا أحاط علمه بأن هذه يسبب تحديا أو تسبب إشكالية حتى لو كانت صغيرة، فإنه غيرته على مملكته يجعله يحل هذه المشكلة بسرعة. هذا هو الفرق بين الكونشسنس وبين التدبير الإلهي. طيب تعال نشوف ماذا يحمل لنا هذا العنوان The Magic of the Gauge Invariance.
I simply want to give you 3 examples, not general proofs, but examples for the role of gauge invariance for Lorentz invariance. the independence of the gauge fixing parameter, psi independence, and also the so-called unitarity of the S matrix. All of these are very important discussions for the consistency of the theory, and they are also really relevant in professional discussions of gauge theories. Let us begin with the first item, Lorentz invariance. So, and here we simply use the example of Compton scattering. Compton scattering involves external photons, initial and final state photon, and those external photons involve polarization vectors epsilon. And the epsilon polarization vectors, they are not ordinary 4 vectors, they have not simple Lorentz transformation properties. Therefore, for processes with external photons and epsilon polarization vectors, it's not completely obvious that a matrix element is actually Lorentz invariant. And so therefore, that needs to be discussed. And the role of gauge invariance comes from the so-called Ward identity, which we have already proven. So the two Feynman diagrams for Compton scattering look like this, and they lead to a matrix element m mu nu times epsilon mu epsilon prime nu star. And the M satisfies the Ward identity m mu nu times k mu and m mu nu times k prime mu, that is equal to 0. And this Ward identity reflects gauge invariance. It's the same similar relationship to current conservation on the classical level, but here in momentum space for a Feynman diagram. So this is the manifestation of gauge invariance on the level of Feynman diagrams, this Ward identity. And now let us look at the role of the Ward identity for Lorentz invariance. So first, the simplest thing is what we have already done, namely we look at the squared and spin-summed matrix element TFI square. The question is that expression Lorentz invariant? And so in this spin-summed squared matrix element, we know that the rule is correct where we replace the spin-summed polarization sum, epsilon, epsilon star, by minus the metric tensor. That rule is correct because of the Ward identity. So, in other words, gauge invariance in form of the Ward identity allows this replacement. And because of that, we get for the spin-summed squared matrix element m mu nu m star mu prime times g mu prime g mu prime. This is manifestly Lorentz invariant because all the expressions here, all the building blocks, have a Lorentz covariant transformation law. Is obviously Lorentz invariant. Okay. So gauge invariance was necessary for this rule to be valid. The left-hand side of the rule is not Lorentz covariant at all, but the right-hand side of the rule is Lorentz covariant, and therefore we can plug it in and obtain a Lorentz invariant squared matrix element. So that proves that the squared matrix element is Lorentz invariant, and the proof requires using the Ward identity. In other words, it requires using gauge invariance. So this is one example of the role of gauge invariance in proving something physically very important. Let us look at another point which is similar. So in more details, you might want to look not only at the squared matrix element, but at the matrix element itself, TFI. What happens in TFI? in TFI, there are these epsilons, epsilon mu, specific to one photon with momentum k and polarization lambda. And so in our discussion of polarization vectors, we saw that this defines actually an equivalence class that we called square bracket epsilon mu k lambda, okay, like this, in our space that we called V two-dimensional, which was a space of equivalence classes of polarization vectors for massless vector bosons. So we defined that. That was section 261. And so the equivalence class basically corresponds to this replacement. Epsilon mu goes to epsilon mu plus some arbitrary prefactor times the photon momentum k mu. That is the meaning of the equivalence class, that if you replace epsilon by that, it's equivalent to the original epsilon. The equivalence class exactly contains differences proportional to the momentum. So this is a replacement that you can do in an equivalence class. And now what you see, if you look at the matrix element for the physical Compton process and you do such a replacement, then the matrix element does not change because of the word identity. So the word identity tells us that each member of such an equivalence class can be used in order to evaluate Compton scattering, and the result will always be the same. So that is one example how this equivalence class structure is compatible with our QED with interactions. And remember, that was always the point. We need these gauge invariant interactions in order for the theory, even including interactions, to be compatible with equivalence classes, and that is what we see here. So this mu nu times epsilon is invariant under this replacement. So it is independent of the representative that we use in the equivalence class. So compatibility with equivalence class structure is again also a consequence of the word identity, in other words, of gauge invariance. And so tomorrow, actually we have 1 minute of time. So since we have 1 minute of time, let me finish this. Let me finish it here. Very good. So what does that mean? Let us now look at Lorentz transformations. As I said, and as you know, the polarization vectors for massless vector bosons, they are not ordinary 4 vectors which have a simple Lorentz transformation law, and we showed exactly how they transform, namely lambda mu nu times epsilon nu of k and lambda is a linear combination of the following, namely of the polarization vectors for k prime and physical polarizations lambda equal 1 and 2 and k prime mu. So that was the result of our section 262, the Lorentz transformation of those polarization vectors which were defined. And so what that essentially means is that the Lorentz, the polarization vectors are Lorentz 4 vectors up to possible additions of momenta. So now if you look at this, such an additional term proportional to the momentum in a polarization vector basically is not meaningful because it drops out if we plug it into the matrix element calculation. Therefore, if you do a Lorentz transformation of the matrix element, the epsilons transform in this more complicated way, but the disturbing momentum drops out, and therefore effectively the epsilons behave like 4 vectors. In mu nu epsilon mu, the epsilons effectively behave like 4 vectors. And in this sense, the full matrix element TFI is Lorentz invariant. And that again is a consequence of what we said before. Ultimately, this is therefore a consequence also of gauge invariance in form of this Watt identity. So you see, in this case of Compton scattering, with external photons, Lorentz invariance is at stake. Lorentz invariance is questionable, and it is true because of the Watt identity. And as a byproduct, we also see the equivalence class structure from before is compatible with our interactions. And tomorrow we look at the other items connected to gauge invariance, and but this is therefore now completely done. Okay, thank you and see you tomorrow.